Hi everyone, my name is Amir Naveh, Head of Algorithms at Classic, and I'd like to share with you a short demonstration of our platform. Let me just quickly share my screen here. So just a very brief overview on Classic. So what Classic does is give an extra layer of abstraction above current gate level platforms such as Qiskit, QSharp, and Cirq, where we enable the user to give us a high level model of the circuit describing the desired circuit functionality. And from this, we can synthesize a specific gate level quantum circuit. So the user would describe the functionality with a model of the circuit, and then this circuit is automatically generated into a concrete instance of a gate level quantum circuit when this is possible. So let's show a few examples of this. So right here, I've prepared a very simple model of a quantum circuit. So I request 4 qubits, a minimum depth of 1 and a maximum depth of 3. And for this very simple example, we're going to do with no optimization. And then I just generate a quantum circuit out of these constraints. And here we can see a circuit complying with all of these constraints. And on the right-hand side, we see a quantum assembly or the specific gates that we put on each of the qubits, the exact instructions. And then, of course, this is only one instance of a circuit complying with these constraints. So if I generate once more, I'd find we get a completely different circuit. Or if I generate again, and you can see each time we get a completely different random circuit complying with all of these constraints. So that's a very simple example. And then let's move to something a little bit more complex and descriptive. So let's say we would like to have a state preparation at the beginning of a quantum circuit where we begin with the 0 state and we now load this probability mass function. So we'd like to have the first state with 5% probability, the second state with 11% probability, and so forth. So what I do here is generate a circuit out of this model. And you can see here that we defined some error metric and a bounds for how many gates this circuit can maximally have. And then this is a circuit complying with all of these constraints. We can also check that indeed we got what we expected. So I can just copy this into, for example, when it's quantum assembly into the quantum experience from IBM. And we can see here that this is 5%, 11%, 13%, 23%, exactly as we requested in the model. Now, if we relax our error tolerance, so for example, instead of 0.01, 0.1, and regenerate, then we can get a much shorter circuit, of course, with higher errors than the one we received before. So this is very useful for many applications. And I would like to finish with an even more descriptive or complex functionality we can achieve. So let's say we would like to have describe in a circuit some arithmetic expression. In this case, a squared minus b squared. So if I just move to the presentation quickly, a squared minus b squared can be implemented in many different ways. So we can do a times a minus b times b, and we can do a plus b times a minus b. And of course, the add can be implemented in many different ways, and we can choose how many ancilla qubits we're willing to allocate to each of these constructs and at what approximations we're giving them. So even in this very simple expression, we have quite a lot of possibilities and descriptive ability. And what we're trying to do here is say, okay, so I've allocated 10 qubits to perform this statement on A and B of size 2. And I would like to optimize on the depth of the circuit. So what I'll do is I'll press generate, and right now in the background, what we're attempting to do is synthesize a circuit complying with all of these constraints and also having a minimum depth. Once we're finished, we can, okay, so we can have, this is a much more complex circuit. This is already a large circuit. And we can see here, one of the most important functionalities we have is the ability to analyze a circuit. So this is the most basic way to analyze. Simply press here, analyze the circuit, and we can see as part of the parameters of the circuit, we have depth of 316. And then we can ask ourselves what happens when we relax the qubit count. So let's say I'm willing to give this construct 12 qubits. So I'll try and regenerate. And of course, I'll get a quantum circuit that maybe has shorter depth because I was able to devote up to 12 qubits. And indeed, I have still a complex circuit, but when I go to analyze the circuit, we can see here that the depth is indeed much shorter. It's only 132 gates to describe, depth for this specific circuit. And this is, of course, only an example. When we'd want much more complex arithmetic expressions, such as you need, for example, in describing complex oracles or many other use cases that use arithmetic. So I hope I've given you a taste of what can be achieved when modeling the circuit and describing the functionality over implementing the circuit at the gate level. Thank you for your time and attention, and I hope to be able to share much more of this in the future. Thank you.